All right, good morning, everyone, and thank you for joining us. My name is Bruce Wallis, and I lead product management for our SR Linux product. So it's not often you get the opportunity to kind of build something from scratch with a ton of pedigree underneath your belt. That was kind of the opportunity we had presented with us quite a few years ago. It was back in 2018, this endeavor started. It's been a lot of fun. I think we've done a lot of unique things with how we've designed the NOS, made it as decoupled as possible, and kind of made it as consumable as possible, whilst trying to make it as open as possible. So there's a lot of as possibles in there. Today, we're going to focus primarily on some of the management and extensibility angles. Of course, we'd love to talk about everything, but we only have a limited amount of time with you guys today, so we'll have to schedule some follow-ups at future NFDs. So to dive right in, Jeff mentioned a problem with kind of this interface iteration. So we as an industry aren't too unfamiliar with iterating at an interface level. And kind of what I've tried to portray on this slide here is, we have a traditional NOS over on the left, and we went through this kind of inflection point a few years ago where we started to move towards model-driven management. I'm sure this is no surprise to any of you. We've all been harping on about these model-driven interfaces. But really, the change here was mostly skin deep in that, if I walk through this diagram from the bottom to the top, the blue kind of bars are meant to be the level of visibility you have into the system. And typically, there was a single monolithic schema that applications would publish data into, or I guess would be polled to retrieve data from and publish into. And we would then build these interfaces on top of it. And as we started to move towards this model-driven world, in some cases, I think some vendors went and did it right and really embedded those Yang models as close to the applications as they possibly could. But the reality is there's a lot of baggage coming into that world. And what it meant is that depending on which interface you come in on, you're getting a certain amount of visibility, and often you have to query multiple interfaces to see everything, unless you're using the interface that is aligned with the native schema of the device. So, if you have a device that uses SNMP trees and OIDs to store data, then SNMP is probably the interface you would use because that's going to be most closely aligned with how the schema is represented. As you started moving towards this model-driven world, you weren't getting all the visibility you needed. So often you were doing multiple integrations, even with just the same single device, in order to see everything. And I'm sure you guys have seen a lot of this. Sometimes some of the information is only available in CLI. Sometimes it's through SNMP. And for some of the newer applications that had been onboarded, maybe you had to access them through one of the model-driven interfaces. So this is what we mean by the interfaces really only being skin deep. There was no real underlying change to the architecture of the NOS itself. And this meant not only are you dealing with that kind of translation tax, and we're trying to get into a world where we can do high-scale streaming telemetry at the granularity we need to make decisions off device. And when you start adding in this tax, imagine you're trying to stream a huge fib off the device, and that every entry in that fib is going through a ton of different serializations and deserializations to get into the format it can be sent to you over whatever interface you're accessing it over. That costs CPU cycles. And really what it impacts is the performance of streaming telemetry, which was a problem we wanted to try and solve for. As we started to look into this, we realized that there was kind of a unique opportunity here to kind of break apart the NOS itself. And this is where we start to get over to the right-hand side of this diagram, where you see we have quite a few different applications. These could be anything from a routing protocol to something that manages interfaces to something that manages LEDs, whatever they may be. And in our architecture, we actually bundle the management description, which in this case is a Yang model, with the application itself. So you end up with these very clean, discrete modules in the system where an application and how it expects to be managed are now joined. So you can imagine that if you are a customer and you want to write an application, and typically agents and extensions to NOSes aren't new, but typically they end up in the bucket of being kind of unmanaged code. You've got a shell script that's scraping some data. It might be writing to a log file. If that shell script breaks, if it becomes important to your workflow, it becomes very, very hard to debug. And not only that, we just added another interface, right? It's a new interface, which is looking at syslogs. So what we really wanted to get to is building out not just the NOS itself and making that turnkey, but breaking it apart, making it as modular as possible. I hesitate to use the term microservices here, but you can kind of imagine a ton of different services in the device that all are kind of functional blocks that you can either take or leave or replace or add to. So as we were kind of tracing this vision, we realized that we needed to start building very clean boundaries between applications. And so this is where we started getting into things like protobufs and gRPC and a pub submodel between applications. And that's what we'll start to see in some of these next slides. But the northbound system definitely doesn't want to see 20 different schemas, right, for the 20 different applications. At the end of the day, our northbound collectors, our automation platforms, they just want to see a network element. So this is where this kind of management layer comes in. It is what is doing kind of the merging of all these different schemas into a single tree, which we can then expose. So this is what we mean by when you build applications on top of SR Linux, they're going to be merged into that schema. So, and we're going to see this in the demo that Erwan's going to show in a little bit, where he'll actually add an application and we'll see it kind of dynamically update the schema. The side effect of all of this is now our model-driven architecture is no longer skin deep, right? We've actually nested it right into the heart of the architecture. So you can do streaming telemetry to any one of these applications. They have the ability to publish data on change. Our architecture takes care of the publishing of all that through a ton of what would be described as, modern model-driven interfaces, whether they be the slew of gRPC services we're starting to see, or through the more, traditional netconf, resconf, and of course, the model-driven CLI. So you're going to see a lot of this in the demo later.
Hey, Bruce, another question here, specifically about the data models. I noticed you have Yang mentioned there, of course. Are those the Nokia provided applications? Are those going to be using OpenConfig data models or Nokia provided data models, or both?
So both is the answer. So we actually really wanted to use OpenConfig, I will say, and we spent a lot of time figuring out how that would work. We really wanted to optimize as much as we could for a CLI user. Obviously, that wasn't our first preference, in that we're typically managing devices through APIs these days. But in order for the CLI to be usable, we needed to have kind of a trimmed down OC model. And I'm specifically talking about redundant containers and config and state containers, things like that. So the answer is both. So we will support both OpenConfig and our own data models. The data models that we have will look and feel pretty much exactly like OC models. You'll notice this as Erwan starts going through the CLI, but they're just trimmed down to be a little bit more human readable. So this allows us to do a very clean, almost one-to-one mapping of an OC leaf to one of our leafs. We will actually in future enable you to do OC-based CLI as well, given all the architecture is model-driven. We have almost a one-to-one mapping. It's pretty easy to let you interact with an OC schema, even from a CLI perspective. So right now it's both. I expect that to continue, and there's a few pretty good reasons for it. The biggest is that we need to continue to iterate the schema that the applications are using. So with the OC kind of being iterated out of our control, we didn't want to have to merge all of that back into the application. So we kind of made a conscious decision. We'll build our own data models. We'll align them with OC as much as we possibly can. This at least gives us some flexibility to build things that haven't been described in OC yet. And we'll still provide the OC model as kind of the stable management schema for northbound collectors that don't want to deal with vendor-specific extensions and things like that. Cool. So let's take a quick look at the architecture, and obviously this is quite summarized. So I'll start from kind of the bottom and move my way up on this diagram. So this is all running on merchant silicon for the most part. And there are a number of different merchant silicon vendors out there, and they have a number of different chips, which typically have different SDKs. So we already were in the realm of, okay, we need a clean hardware abstraction. And this is what we call our extensible data path. Really, this is pretty simple. It's just two layers, kind of a northbound interface towards applications. And this is what means, none of these applications have to care what type of hardware they're running on. They're interacting with the same kind of common layer. For those of you who are familiar with Sonic and Psi, you can imagine it's pretty similar to that. You have kind of a northbound interface that's pretty standardized that all the applications interact with. And underneath that, there is kind of an ASIC dependent layer, which will be plugged in based on the type of hardware we're running, and we'll do the translation to whatever specific SDK instructions we need. On top of that, we have this kind of infrastructure layer, and this is the layer we really wanted to open up for everybody to consume, and that is a big part of why this NetOps development kit exists. And really, it is kind of this model-driven management architecture, which Erwan's going to show later. Pub/sub state sharing. So, I mean, you've all seen similar architectures where you have a database and you have a ton of applications that sit around it. They can publish data, they can subscribe for data. This is no different to that. The only difference I will highlight is that the kind of the messages that are being shipped around are actual protocol buffers or protobufs. And what this means is, you as an end user can actually decipher the messages that we're sending between applications. You can subscribe to these topics yourself. If you're interested in what's going on in the fib, you could subscribe to that, all at a very low, native level to how the architecture is functioning. This is all built on top of a standard Linux kernel, so we didn't make any changes there. We're using an upstream kernel. Does mean we have to do a lot of things in user space, but it gives us the flexibility of allowing a customer to kind of take control of their own destiny, potentially patch the kernel. We went through a ton of scares, not so recently, but recent enough that we're all still a little scarred from them, and shell shock and heartbleed. And, we as a vendor, of course, had a ton of customers come to us and say, first, am I exposed? Because, quite often we didn't expose the type of kernel we were using. And when can I get a fix? So this is to try and alleviate some of that, to give some more flexibility to customers that want to react faster to these kinds of things, and potentially, if they have their own hardened kernels, to use them in place of our own. On top of that, we have kind of a bunch of different network applications. And again, every one of these is kind of a discrete module in the system. So you could decide that you don't want BGP. That would be strange, but valid. And you could take BGP out. You could replace our BGP stack with another BGP stack if you really wanted to. Now, these are all kind of crazy examples because we stand by the performance and reliability of our BGP stack, but it gives you an idea of kind of what the architecture is capable of, in that you can kind of take pieces that you want, you can leave pieces you don't. And of course, this reduces blast radius in the event of bugs and things like that. And you can add to it. So that's kind of what I have over on the right-hand side of this diagram, where we have, this fib agent and this imaginary telemetry agent, which have their own data models. And they're all being kind of abstracted and merged together through this management layer and then exposed through the northbound interfaces. So looks kind of like your typical NOS, I would say, but there's a lot of devil in the details. And what really makes this, I'm air quoting here, open, is that the use of protobufers between applications, the use of gRPC as the means to interact with the services themselves. We'll see that the NDK actually ends up being like a gRPC aggregator for the system. So any one of these applications can say, oh, here's this gRPC service I will support, expose it through the NDK, which gives us a very, very clean interface for customers to interact with, all using protocol buffers, of course. So we get a ton of backwards compatibility and a slew of programming languages there to allow them to iterate on the system as much as they see fit. And really, this is to try and fit into this whole NetOps model, where we want customers to be able to kind of take control of their own destiny, to make the NOS kind of fit into their network, as opposed to kind of everything around the NOS kind of augmenting itself based on what the NOS exposes and how it exposes it. This is just to try and automate a lot of those small nice to haves, which we typically see as mostly workflow optimizations. And you'll see a pretty cool example of one of these in the demo that Erwan's going to show later.
Hey, Bruce, I got a quick question for you. So what about the communication between the applications? How is the interface going on between those?
Good question. So that's I did skip over it kind of intentionally because it's a bit of a rabbit hole. This impart database that you see in the middle of the slide here, we kind of made a bit of a hard rule for ourselves that we didn't want to have kind of shared memory interfaces between applications, proprietary interfaces that a customer could not see or interact with. So we have kind of two ways of communicating with applications. There's one side, which is on, the streaming telemetry. This is a northbound collector coming in, establishing, a subscription to a path that happens to be supported by a certain application. What happens there is that we actually build a channel across our impart database directly to the application. So you end up with kind of a clean back pressure mechanism for all the paths that you're subscribing to. So that's kind of on the telemetry side. And on the actual kind of state sharing, how do applications themselves do IPC, they would basically create topics inside IDB and publish protobufs to those topics. So, IDB is just seeing binary blobs. There's a few reasons we do that. But the applications themselves can simply subscribe to, I don't know, IPv4 routes, for example, which would be any application that is contributing IPv4 routes. Or maybe you want to only select the best routes, in which case you would subscribe to Fib Manager IPv4 routes. So you have a lot of fine-grained control on the kind of data you want to receive from the system, what the application wants to receive from the system in the form of IPC, but all of that communication goes across our impart database. So this gives us kind of an aggregation point where anybody can tap in at any point and say, I want to listen to that because that's useful for my workflow.
Hey, Bruce, this is Jeremy. I've got a question to that point. I'm kind of familiar with this idea and this architecture. So if I was writing an app that wanted to intercommunicate with other applications through IDB, does IDB represent and maintain the state of a database, or so that when my app comes up and I say, hey, I want to know what was the state of what was going on in BGP or LLDP, so that I can, build the state of my app if it, restarts or fires back up? Or is IDB more of a pub/sub mechanism that doesn't maintain that kind of state data?
Good question. So it does maintain data for the exact reason you describe. So we wanted to allow any one of these applications to appear in the system at any point, to potentially disappear and come back at any point, and to reconverge with the system state. So the way IDB works is it maintains basically a ton of different topics with a ton of different key vowels inside them, and each one of those keys we maintain latches for which applications have actually received this update. So we can intelligently propagate state based on where an application is actually up to in terms of catching up. So this means a couple of things. It means that if you have, let's say, the classic example is like an LED flapping, right? So you have an interface that's going up and down, and you now need to set the LED to green, amber, green, amber, green, amber. If your process that was setting the LED to green, amber started to get out of sync with the rest of the system, typical message bus architectures would just continue to throw messages at him, and maybe he would catch them every now and then and update his state, but he would eventually get behind again, and in a lot of architectures get disconnected, restart, and come back. In our architecture, because we're actually maintaining what we've sent to him, we know what he has received, and this is just using simple, Unix domain sockets and back pressure and all that good stuff. We can only send him the updates that he needs. Even if a key flapped 100 times, at the time we send it to him, we send him the latest update. So the system is constantly doing this kind of coalescing and converging. And at any point, one of these applications could disappear, come back, reconverge with the system state, and only the state that he has published would be impacted, because, of course, at that point, we can't validate that that state is good. There's a few cases where we're even starting to mix up that model, where we'll allow applications to kind of store state and say, I'm going to go away and potentially upgrade, right? And come back and then converge with their own state and do a bit of a sync mechanism with IDB. So I think that answers your question.
Yeah, it does. Thank you. I have a follow-up though. As these types of systems present a data store, then if I'm writing an application and I want to make a set of changes into the database, does it allow for the kind of commit rollback model that some of us are used to in network operations land, or is each write to that database kind of its own little thing? Can you do that kind of group commit rollback mechanism with this database?
So we do support configuration transactions, and they will support things like commits and rollbacks and all that good stuff. That is occurring at a layer higher than the database. So within the database, I mean, it works kind of similar to, you can imagine very similar to Kafka in terms of how topics and things are laid out. So we don't support commits and rollbacks from a database perspective. It's not really that kind of database. But we do support it at the management layer, and we'll actually see we'll see some of this later, I think. I don't know if Erwan actually is going to show this, but we do this at a configuration layer. So whenever a transaction comes down through the management layer, it will hit what we call our management server, and it will basically push out those changes to every one of the applications. So it's the one that kind of has the converged kind of schema and all the different Yang models. So it knows which application owns which part of the schema. It'll push that down to those apps, and they have the ability to say, I don't like that for whatever reason, and that would fail the commit, and then it would end up with a full rollback to whatever the state was before then. All of this only occurs at the configuration management layer. It doesn't occur within the database.
Hey, I got a question here, kind of just about the usability of applications and the portability of applications, stuff like that. So from a market standpoint, do you actually see non-FANG, non-hyperscaler kind of people wanting to be able to write their own applications? Or is this more of a, if you build it, they will come scenario where you're building it and hoping that people will be like, oh, cool, now we can do this? Because, you know, it sounds like a lot of effort to write, you know, an application for this, and maybe that's worth it, but I'm just curious, what kind of use cases are you seeing where that's desired, if you are seeing them yet?
So yeah, I think it's a little of both, honestly. No one really thought about the idea of writing applications that could kind of publish their own state and populate their own schema and have that streamed out. So there was a little bit of build it and they will come, and this was as Jeff kind of alluded to, in kind of a collaboration with one of the design partners. They had a lot of use cases where they wanted to do this, but these use cases aren't necessarily that complicated, right? They're not, I want to build a routing protocol because I want to do things differently, although we have had people do that. They're more along the lines of kind of what you'll see in the demo later. They're kind of small workflow optimizations that aren't actually that difficult to write. And in fact, the application that you're going to see later was not written by a developer, right? It was written by a product manager. So you'll see that, you know, you don't need to be a full-fledged developer to onboard these applications. They're not quite as complex as you might imagine. A lot of that is coming through the NetOps development kit, which is a very, very easy to consume gRPC service. So I think there's a little of, you know, people now that they understand that this can be done, and it can be done in a way that can be consumed northbound, we're starting to see quite a few different ideas. I actually have some use cases later on in the deck to kind of show you some of the examples we've seen. Some of them, like I said, are very, very simple workflow optimizations, you know, allowing you to do a GNMI set on a leaf, and then there's an application that's listening for that GNMI set, and it will just go and scrape a bunch of data and push it off to a northbound system. That's a totally valid application. There'll be some more complex applications that are doing things like Pixie servers. Maybe you don't want to have a Pixie server in your data center anymore. You want to offload that into the network. That's one of the use cases I have later. So they're actually pretty simple applications. They're not as complex as you might imagine, although they could be, right? You know, the sky's the limit here. But so far, we've seen simple workflow optimizations that have a real world impact on how the data center is managed and operated. That's where the kind of the most value seems to be for these kind of things.
Bruce,
okay.
In addition to this, a question: can anybody write an application and deploy it freely, or are there some limitations, security measures, and everything else?
Anybody can write an application and deploy it freely. The deployment, of course, is very controlled, right? You need to have read-write access to the NOS, for example. So there's security via RBAC, you might say. The applications themselves, Nokia is not vetting, right? So some customers that are more security conscious probably aren't going to go and grab, you know, off-the-shelf open source extensions and just run them. That's totally valid. But yeah, for now, simple RBAC and the ability to interact and write to the system is what is needed to onboard them. Now, we got the question earlier of where the kind of routing protocols come from, and you know, Alcatel-Lucent. That was a good throwback. So absolutely, kind of the first 18 months of the project were spent trying to figure out how to bring these applications that we've already written for SROS, being the protocols, and bring them into this architecture in a native manner. So we spent a lot of time doing this. We didn't want to break our single source of truth for the protocols being in SROS. So the protocols you see running in the NOS are going to be the same protocols you would see in SROS. So our customers are benefiting from, you know, the hundreds, millions of hours of tests that we've run against SROS, the 20 years we've spent in the market. I think as of Q4 last year, we're #2 globally in IP edge routing. So for those of you at home who haven't heard of Nokia, we are very, very big in routing, and our protocols your packet is traversing one of our routers as you listen to this right now. So we've spent a lot of time in the WAN space. We definitely didn't want to break our link to these protocols. So as features go into SROS, as they go into SR Linux, because we have had a couple of cases where that has happened, we're getting them across both operating systems. All right. I'm going to talk quickly through the NDK and then some examples, and then through our CLI, because I want to spend a little bit of time on that because you're going to see it in the demo. And then I will hand over to Erwan to close us out. So the NetOps development kit is, I kind of alluded to this before, it's kind of a gRPC aggregator for us. You interact with it in whatever language you want. The fact it's using gRPC and Proto means we're not binding you to a specific language. This was the first complaint we had from our customers, is that they didn't like the fact that the current kind of SDK implementations required them to write in C++ or Python. And as the vendor continued to iterate on the SDK, quite often they were having to do the conflict resolution for libraries that had been upgraded, that they were using, but were different now. We wanted to get away from the kind of the coupling of the application to the version of the SDK, and protocol buffers and gRPC give us a very, very clean mechanism to do this. The NDK, like I said, acts as a gRPC aggregator, and the most important service that I would say that is exposed here is kind of the config service, which allows you to not only receive configuration through your Yang model being hit, but also to allow you to publish state back to the system. Of course, you have access to also subscribe for any information you need for whatever your application needs to do, and we expose it through the northbound interface. Okay, a couple of examples of applications we've seen. So this one is pretty simple. I actually showed this during our launch, which is a simple application that monitors a bunch of different statistics in the system. So it's doing, GNMI subscriptions locally, ingesting a bunch of different traffic statistics, ACL drop statistics, errors, that kind of thing, and had a configurable threshold where you could say, if I have a delta of 5% or more between traffic I'm receiving and traffic I'm sending out, allowing for in-flight packets and all that, all it would really do was just publish whatever the last delta was, whether it be 5%, 6%, whatever it was, and then set an alarm state. And so what this meant is, you could do this kind of thing off box, right? There's nothing stopping you collecting a bunch of stats and crunching this off box, but this allowed you to distribute that problem into the network. And all your collector now has to do is monitor that alarm state. And that alarm state means that you're dropping more traffic than you were expecting on that specific device. So a nice way of just distributing a task that you would typically do off box, but can easily be done on box and helps you distribute your workload, scale your collector better. A ton of advantages of doing this kind of thing. Another application we've seen written was to remove the need for kind of your Pixie server in the network. So, typically you'll have maybe a compute per rack in like extreme scenarios, but maybe a compute per row that is just providing images and bootstrapping all the different computes. Well, why not do that in the network? Like your Tor is sitting above every one of those racks. Why not run a DHCP server there? Why not run a TFTP server and a web server so that you can pull down images? So not only are you now not burning a compute to do this kind of thing, it's actually more efficient because you're localizing it within the rack. You publish all the information about which images computes are booting into streaming telemetry. You can even interact with the images the computes are booting and change them via a GNMI set, for example. So again, just showing like a pretty simple workflow optimization, but with a very easy to measure tangible OpEx saving. And we're no longer burning computes to do this kind of thing, which is not really a compute intensive task.
Hey, Bruce, with this example of using Pixie running on the actual device, I know other vendors have kind of approached this kind of problem space by letting you run like your own containers on the devices instead. So I'm kind of curious, what gain does all of this tie into like the IDB and this message bus and all that stuff? What do you gain using all of that to run something simple like a DHCP or Pixie server that, in my very limited understanding of this, wouldn't need to know about all of that state about port LEDs and all of that fun stuff?
Yeah, for sure. So the big thing we see being used here is the management infrastructure. So now you can interact with these servers using the same management interfaces you were using for BGP, for example. So In this case, they're not using much from other applications, other than you could, check the fib to make sure you end up with a route and, populate that into state potentially. I don't think they were actually doing that. That was just kind of an example off the top of my head. Really, the advantage they were seeing here is now they had a single interface to interact with the device and to interact with those servers too. So like I said, there's nothing stopping you from doing this on any Linux-based NOS, right? You could run a container and it could do all these cool things. You could maybe, write ACLs to attract traffic to the slow path. There's ways to solve for this, but how do you manage that server is the question. Typically, it's going to have its own management interface. You're going to have someone log in, have to, log into a container, look at some logs. In this case, all of that is exposed through streaming telemetry. So you know the state of the server, you know how many clients are booted against it, you know the last time it received a message from each one of the computes, you know the image that was being served to those computes, and you can interact and change all these things via the same management interface you're using to configure BGP. That was the big advantage here.
So do you find that the people who are like wanting to run Pixie and stuff are typically the same groups that run like BGP and stuff? Because it seems like with a lot of organizational silos that wouldn't be the same group people.
Yeah, I don't think it was in this case either. I think they were two separate teams. In this case, through RBAC, we could allow the kind of compute team to interact with the device and only mess around with the things that they were running, and the network team to manage everything else. So they didn't care so much about where it ran. They cared about who had the rights to configure it.
A follow up to that one, just really quick. When you keep saying the management interface, it keeps sounding like an all or nothing type thing. But with RBAC, you are saying that there can be a more granular and a more siloed approach to management of those things. Because comparing that to Chris's example of containerization, you can get extremely siloed with the management. Can you do the same thing with the management interface here?
Absolutely. Yep. We can filter down to a single leaf within the Yang if that's what you really need. Or you can have access to the full root. So all of the RBAC is, of course, based around the Yang schema. So that's how we enforce the RBAC. So you have the ability to decide how granular or how loose you want that RBAC to be. Okay,
thank you.
So I'll talk quickly through the CLI. And really this, I'm sure most people on here aren't interested in hearing about CLI for the most part. It's not super interesting. We have actually done some cool things with the CLI. The CLI is actually open source. So it's written in Python and it's just interacting with our management server, which exposes a gRPC service. So they're just protocol buffers. And really we were trying to solve for a problem where you have someone who wants to add or change the way a show command looks. And typically we as the vendor product manager have to figure out, okay, does this address a wider market? Is this going to be useful to everyone? Is it going to actually detract from what the show command is trying to do? We have to kind of always cater to the median. We can never cater for a specific use case. And we really wanted to solve for that with the CLI. So not only is the CLI all model driven, but it allows full extensibility in the form of these kind of Python plugins. So you have the ability to, change the way a show command looks or feels. You have the ability to add show commands. You have the ability to add anything you want, really. Python's pretty extensible. And now, it's to follow this whole model of we want the NOS to look and feel how the customer wants it to look and feel, not how the average customer wants it to look and feel. And that is really what a lot of the different things we've done have kind of been in search of.
So, hey, this is Jeremy. Got a question about the CLI open source thing. I'm pretty interested in that. I do build a lot of tools and we build a lot of CLI tools and we write a lot of, Python. So I think what you're saying is that Nokia has somewhere in GitHub a repo where I could, download this essentially a CLI mechanism. I'm presuming there's also a set of tools that would kind of crunch through Yang models, and the CLI tool would then use that kind of infrastructure.
Exactly.
The database that the CLI would manage, whether that's IDB or this other management database, is that also in the open source or available as a standalone entity so that as a developer, I could, develop my CLI external from the entire stack of the OS, kind of like have a little standalone dev environment that doesn't require the whole stack of the operating system to be running. Does that question make sense?
Oh, I see. Yeah, I think so. So, I'll go back to the first. So this isn't actually in GitHub yet. It will be. We're going to publish both the open source CLI and a ton of different protocol buffers. That's actually on me. I've been meaning to do that for a while. I just haven't gotten around to it just yet. So it will be put up. We don't actually have a ton of different databases. We have different representations. So management server will hold on to kind of an internal database of sorts, but where it actually stores data is in the IDB. So we don't end up with this kind of duplicative, state. We do allow you to run as trimmed down an OS as you need. And, we actually do have a public container image of SR Linux that we're going to be releasing very soon. I was hoping to have it ready for networking field day. We didn't quite make it. That you can just run it in a container. You could trim it down so it doesn't run any of the protocols. You can just strip out applications as much as you need. And then you could interact with it from there. It is very much linked into the management server, gRPC, and protocol buffers, though. So the CLI really is just interacting with another application, being management server, which is exposing a gRPC interface. The proto for that, we are also going to be open sourcing, since you can kind of reverse engineer it from the CLI anyway. So I don't know if that necessarily solves the case you're thinking of. I don't fully understand it, but I think you're going to have all the tools you need in order to iterate, to write some of these extensions yourself, potentially even use this for another entirely different use case, with a management server being as this kind of Yang aggregator for you.
Yeah, that is actually the use case I'm thinking of. So I might just follow up with you, on that particular topic, so we don't rat hole here. Thank you.
Yep. I mentioned the CLI was open source. You can kind of see over on the right how the tree gets built. So the CLI takes a ton of different sources of information. The most important one, of course, being the Yang models that are fed from management servers. So you have the ability to interact with the schema through the CLI. The entire show tree is just a ton of different plugins. Traceroute is a plugin, ping is a plugin. You can reverse engineer, change any of these however you see fit. In most cases, we're just dropping them through to kind of the Linux variants of those commands. We do also have some really cool aliasing framework. I don't know if we're going to get time to see it today. And also the ability to tune the CLI to look like how you want it to look. So you can imagine, an RC file for a ZSH or Bash or something like that. We have something very similar here that allows you to tune how things look, what the prompt looks like, what information is displayed, all that good stuff. Again, to try and bring the NOS as close to what the customer wants it to look like, as opposed to what we think it should look like. And here's just an example of one of those CLI commands where we have some off-box database, and we simply want someone to be able to log into the device, run this validate topology command. This command doesn't exist, but someone wrote a plugin and added it. And it would phone home, it would look at the external database, it would compare what the database thought the NOS's topology should look like versus the LLDP topology, and flag it to the engineer. So a very simple way to log into the device. Are all my physical links as they should be? Run one command, does a bunch of phoning home, figures out what it should be, compares it against what it is, and shows you the delta. And this is just a bit of a wrap up. So you're going to see some of this lifecycle management in the demo. Yang integration, I've harped on about that throughout the entire presentation. I don't think I need to do that anymore. And of course, we have our Python-based CLI. So again, you're going to see some of this in the demo. Any questions? I think this is my last slide. Yeah. Otherwise, I'll hand over to Erwan.
Whenever I sit down at somebody's Emacs system, I find that it's unusable because they've customized it their way.
Yep.
How are all these plugins avoiding that kind of syndrome?
Well, we allow you to add plugins globally. So you can have, one team that is like, these are the plugins that we're going to deploy in the network. We allow these plugins per user as well. So typically, the person that's logging into the device is the guy that's interacting with the device. There's some cases that's not true, of course, but in a proper real world scenario, you're logging in as yourself. You get to decide based on your environment what that looks like. You never have to use what someone else has kind of put in there. So you can imagine it looks like defaults for the most part. And per user, you have the ability to override those defaults. So We do have concept of kind of global plugins and per user plugins and global aliases and per user aliases. So you can decide how far your customizations kind of seep into everybody else who is using the system, or how little they do. You have the full power there.
Okay. So it sounds like it's basically like Emacs on Linux.
Well, yeah, I think, customizability doesn't go without change, right? So in order to embrace this, we do have to acknowledge that people are going to make it look how they want it to look. At the end of the day, you have the choice on, do you want to, have these changes kind of ripple through every user of the system, or do you want to, when you log into the device, have just the defaults and it looks exactly, how it would look out of the box? You get to decide. There are downsides to extensibility. There's no question there, but there's a lot of flexibility. I think there's a lot of upside too. And these are some of the
basically lots of rope. Your choice as to what to do with it.
Yeah, exactly.
All right, thank you.
Cool. Okay, I will hand over to Erwan.
Thank you very much. All right, hi all. My name is Erwan James. I'm our IP architect for Nokia. And I'm going to try and walk you through a live demo of everything that Bruce and Jeff have talked about so far. Okay, I'll try not to spend too much time in slides, but I do have to do a little bit of context setting and just kind of environment setting so we're all on the same page as I go through this. Basically, what I'll do in this demo is I will do a bit of a deeper dive into an NDK application, right? So, Bruce harped on about those applications. There were some good questions about the complexity of an application, whether it could be simple or complex, and how hard it was to onboard. So I'm going to walk us through actually deploying an application onto SR Linux. We'll look at what this application actually does and some of the value it brings. So that ties us back again to some of the questions we heard earlier. And then finally, we'll look at how that interface, that new application is interfacing locally on the device with the CLI that we've talked about also, as well as our northbound interfaces. So as I go through this, don't hesitate to stop me and interrupt me for questions. I do tend to get a little bit excited about some of this stuff, and I can ramble on. So do interrupt me as needed. Okay, so let's go through our demo environment, just set the stage a little bit. So the first thing is we are using a single SR Linux switch, and in this particular demo environment, it's going to serve as a top of rack switch. In this case, it is going to be serving below it a set of compute nodes. Now, these compute nodes will be running as part of a Kubernetes cluster. And so we also have a fully functional Kubernetes cluster with, in this case, is quite scaled down, only 3 compute nodes. These 3 compute nodes are talking to the top of rack switch. And one thing I'd like to mention about this Kubernetes cluster is we're running something called Metal LB. If you're not so familiar with Kubernetes, what ends up happening is when you deploy an application in Kubernetes, you have the option of exposing this application to the outside world through what they call a service, and then furthermore exposing the service through an external IP address. If you're deploying your Kubernetes application in a public cloud, you typically leverage the public cloud's load balancing infrastructure to kind of expose these services and these external IPs to be reachable from the outside world or other applications amongst your environment. When you're deploying on-prem, there's multiple options on how you expose some of these external IPs for that are servicing these applications. But one of the ways you can do this is something called Metal LB. And now the way Metal LB works is, and it stands for Metal Load Balancer, is that whenever an application is deployed, and in Kubernetes, you have a service assigned to this application, and you're exposing this service, meaning you want to be able to have this application available from outside the Kubernetes cluster, from an outside world. What Metal LB will do is it will take this prefix that you're assigning to this application, and it will advertise it to the top of rack switch using BGP. So you have a BGP peering session from every one of your Kubernetes worker nodes to your top of rack switch. And as you grab an application and you expose it, you're assigning a prefix to this application, you're advertising that application from any of the computes that is hosting an application pod, right? So you can imagine if you're scaling out an application in my environment to 2 of the 3 worker nodes, 2 of my worker nodes would advertise my application service external IP address to my top of rack switch with a next hop of itself, right? So you would see in your route table in your data center fabric, to reach this prefix, which is assigned to an application, I have 2 next hops. And so what essentially you end up doing is, you're essentially doing, poor man's load balancer by leveraging ECMP in your data center to load balance traffic to each of these compute nodes for this given application. So just a little bit of context behind that. And then finally, in the environment, we have a telemetry collection stack. So in this particular case, we're using GenomeIC as a GenomeI collector with Prometheus to store the data and Grafana to display it. So that's just to show kind of the interaction with the northbound interfaces. So before I jump into what the application that I'm going to deploy does, I'm just going to talk through a bit of a problem statement, which comes with this particular environment that I've set up. You can imagine in this case that you could deploy an application across your compute nodes. Your compute nodes in this case are participating with the network in that they're advertising that external IP address to the data center fabric. And you could run into a scenario where the routes, the application gets scaled out to all 3 of my nodes, for example. The routes get advertised in my top of rack switch, but then my top of rack switch, for whatever reason, only installs routes for 2 of my 3 compute nodes, right? Whether that be, fat fingering a config template. We're trying to avoid those things with things like Fabric Services Platform, but these things happen. Or potentially a scaling issue where the top of rack switch is not able to install any more routes in the fib. There's multitude of reasons why a route could get advertised from your compute node, but not actually installed in the top of rack switch. So in this particular scenario, you run into a scenario where your application development team would look at their Kubernetes environment and they would see that the application scaled out to 3 nodes. All 3 nodes advertise the route, everything looks good. From the networking standpoint, you would see there's reachability to that prefix because it's in your route table. What you don't know is you have a bit of a degraded service scenario where the network is actually not serving the traffic to all 3 of the nodes that are serving the application, right? So in this particular case, you could run into a scenario where, first of all, how do you detect this particular problem? One is obviously if the user is complaining about a particular performance issue on their application, or maybe you have application metrics, which are now starting to trigger some anomalies in the performance that is expected by the scale out of the Kubernetes cluster, which is not lining up with the performance they're receiving, right? And so in this case, that's kind of the problem statement we're starting in this demo. And when I jump into the environment, this is our starting point. We're actually starting from a point of failure, a point of a degraded service. Okay, so in comes our application, right? So, Bruce and I worked on this application, and we tried to make it try and solve this problem the best way we could, right? So what we tried to do is have an application that would run on this device, which itself is going to speak to the Kubernetes controller API. Okay, so this application is going to subscribe to Kubernetes. It's going to understand the Kubernetes view of the world. It's going to subscribe to our NDK on the local device, and it's going to subscribe to the fib, right? So we're looking for fib changes. And really, its goal is to try and correlate that information, right? And we've created a Yang model for this application to populate some of that state. So we're going to try and expose some of that Kubernetes view into the network operating system. And we're going to expose the result of these comparisons and checks to make sure that for every compute node, which is hosting the application, we have a corresponding fib entry with the next hop of that compute, right? And that's what it's looking for. Now, we're going to leverage everything that Bruce talked about in that once we bring in this application on the device and we bring in our Yang models, you'll see in the CLI that we have access to the application state that we're gonna populate, but as well as us being able to expose that northbound through our GenomeI interfaces. Okay, so if you can see my terminal session, on the left-hand side here, I have a red tab. This represents my compute view of the world, my Kubernetes cluster view of the world. And on the right-hand side, we have a blue tab, which is representing my top of rack switch SR Linux view of the world. So let's take a very quick look at our environment. So on the left-hand side here, I'm going to just look at what we have with regards to our application. So as I said, the application is already deployed. So I can do a quick show of that. Okay, so very simple application. I deployed the, essentially the hello world of Kubernetes applications, the guestbook application, which if you look at their public documentation is probably the easiest and simplest application to deploy. Very simple. It has a back end, which is a MongoDB, and it has a front end, which is just like a guestbook application. that allows you to sign a guest book. You can see here that we have a single node pod deployed for our backend, and we have scaled up our front end to 6 pods, right? And there's 6 pods are spread out across my 3 compute nodes, right? So if I do a get pods, we can see here that we have the front end application, and that's running on 3 of my my computes, which I had shown earlier. And lastly, we have services. What I've done is, obviously, I want this front end application to be exposed to my world. So I've created a service. And what's really important to look at here is this front end service. It's of type load balancer. And what's important to look at is this external IP address. And this is the IP address, the prefix that we're going to advertise to our top of rack switch. It's a prefix that every one of our computes should be advertising to the top of rack switch and propagating to the fabric so that we can ECMP hash the traffic destined to this prefix to each of the compute nodes, right? So this is our scenario. Now, if we take a look at that same application deployed from the switch and the network standpoint, we're now looking at SR Linux. So I'm just going to do a quick run through here and look at our BGP neighbors, right? So in the environment, as I said, we have 3 compute nodes, and then here we see that we have 3 BGP peers. We're all established. We're actually learning some of the routes also, right? So from an environment standpoint, that's looking pretty good. And in the CLI, we also look at the route table. Again, it's a very scaled down version because it's only a single Tor for me. But here's that prefix, right? Here's that prefix that was advertised. If you go back to the compute view of the world, there's that external IP address, which we are exposing our application through. And here we see it in our fabric. So, for all intents and purposes, it's in our route table, so it's reachable from the outside world. I can now reach that application through my data center fabric. Now, what you'll notice here is on the next hop side of things, we have 2 next hops, right? And this is where we introduce the problem. From a networking standpoint, we have reachability. We have 2 next hops, so we can reach that prefix. From a application deployment standpoint, all of my application pods are deployed. They're scaled out across 3 compute nodes. There's nothing to indicate to me that there's any sort of issue with my deployment of the application. What we do find out is that obviously the application performance is degraded, because if you try to reach that prefix from the outside world through your data center fabric, you would get ECMP hashed or load balanced to 2 of your worker nodes rather than 3, right? And this is kind of our problem statement. And so what I'm going to do now is dive into bringing on Kbutler application to try and remedy this problem, right? And this is just kind of a use case we have for a very simple application, which will hopefully bring some context to the network world to be able to troubleshoot this issue and be identified of a degraded service. Okay, so we look at the route table. I was just talking the problem statement, and at this point, I was going to bring on our application finally. So let me just do a couple of things on SR Linux before I actually bring on the application and show some data relating to what Bruce was mentioning earlier. So I just did a show system application. This is showing us all the applications running on SR Linux. And you may see some familiar names here, right? BGP manager, self-explanatory, BFD manager, ACL manager. And so as Bruce mentioned, we broke out all the functions into separate applications. One thing you'll note here is BFD manager, for instance, is not running. It doesn't have a PID because it's waiting for a config, right? And this is part of the stuff that we can do in SR Linux with regards to controlling which applications run and when they run, right? And then the most important part of this is showing you that there's no application here called Kbutler because I haven't yet installed the application on the device. So let me just go ahead and do that. So I'm going to jump back into Bash. So I was in the SR Linux CLI shell, but now I'm in a Bash shell of the same device. I've obviously pre-copied over my application here. Let me just talk quickly about what makes up an application for SR Linux, right? So an application for SR Linux is made up of 3 major components. The first one obviously is the binary, right? The actual application itself. So in this case, the application was developed in Go. And so we have a binary that we created from this Go application. Of course, you can develop your application in any language you see fit, especially since it runs on Linux. So anything that you want to compile and run as a binary on Linux, you can run on this application. It goes from Python to Go to Java to C++, whatever you see fit. So there's our Kbutler bin, right? In our case, it was developed in Go. We also have the second major component of an application running SR Linux is the Yang data model, right? So we've also created a Yang data model. It's called kbutler.yang. And this is because in our application, we want to store some state, right? So we want to go and retrieve data from the Kubernetes cluster. We want to understand what services exist from the Kubernetes world. which Kubernetes namespace they live in, any external IP addresses they're assigned, all that information that's coming from Kubernetes, we want to store that in some sort of state. So we've created a Yang model. It's not complicated, right? So working with Yang is fairly simple. It's pretty simple. You can see it here. And this is just describe what that data tree is going to look like. And then you'll see that our CLI is going to dynamically read this and generate a CLI for it, as well as expose this using our GNMI northbound interfaces. And lastly, we have what we call a app manager configuration file. So app manager is an application you may have seen in that list earlier. As the name may suggest, it manages the application. It's what's in charge of understanding which SR Linux applications should be running, when they should be running, how they should be running, if they need to be restarted, stopped. It's all managed through App Manager. So App Manager looks at this configuration file for this application to get more information about it, right? So if we take a look at this YAML file, some very important commands in this, or parameters starting this YAML file would be, for instance, the path, right? So it defines the path of the binary. So where is this binary going to be launched from? The launch command is self-explanatory. It's how the application gets launched. Obviously, in my case, I'm passing through some environmental variables and some config files that are related to my Kubernetes cluster. And finally, I'm launching the actual binary here in a specific namespace, right? So this is what App Manager is going to do to launch my application. Search command is what App Manager looks for in the process list to know whether my application is running or not, right? How does it know if the application is running and what it's supposed to do? If it isn't running, it needs to define it. So that's how it does that. And then finally, there's some more parameters around failure thresholds. I can dictate through this YAML file what I want the App Manager to do in the event that my application fails, right? Do I want my App Manager to restart it? You know, how many times do I want to try restarting it? Do I want it to stop restarting it at some point? Maybe my application is so critical that I actually wanted to reboot the box if my application fails, right? You have that type of granularity and control if you want to. And finally, where can App Manager find the Yang modules, which are used by my application to store state or configuration, right? So just the path for my Yang. So from here, all we have to do to install an application is move these folders to some very specific folders within SR Linux that will tell App Manager that it should try and load the application. So in this case, I'm going to copy these folders into etc SR Linux. So this is just where we place applications, and I can jump back into SR CLI. Okay. So again, show system application. We see that there's no kbutler there. What I'm going to do is ask App Manager to reload. So I'm going to ask it to go and see if there's any new application it needs to be aware of. And it's going to look for that YAML file that I just talked about, right? So I've asked it to reload, and now I can go look at my show system application. Notice now in the application list, we have an application called kbutler, right? And the application, it has a PID, and it's in a running state. So App Manager went and read that YAML file. It launched the application as expected, and now I have an SR Linux application running as part of my operating system. Now, the next step of the application is to make sure that we're actually reading that Yang model and we're generating a CLI and we're generating northbound interface connectivity to that application, right? So I'm going to enter my state data store, and you'll notice now that as I start typing K, whereas before there was no knowledge of kbutler inside the CLI, I now have the ability to the CLI is now showing me that it's actually suggesting to me that there's actually an auto completion for kbutler. So I can tab complete that, and it will show me anything from it. So I'm going to do an info from kbutler. So I want to dump the data from kbutler. And here's what the kbutler is actually showing me, right? So all these different leaves we're looking at here, those were all defined in the Yang model. And so what is this application actually doing for us? Well, it's showing us which controller. That's the Kubernetes controller it's talking to. It's discovered that it's got a service called front end, that it lives in the Kubernetes namespace called default. And you can tell right away here that this application is actually telling me that my application service is degraded, right? So I've now brought some Kubernetes context into my network. So as a network engineer, if I logged into the device, first of all, I could troubleshoot by looking at the CLI as I'm doing here and see a degraded service. But this information is actually also available via our GNMI interface. So now you can alert on the fact that a service is degraded. So your switch has a clear understanding of what's sitting below it in the computes, what networks are supposed to be advertised to it and from where, and it can compare that to its actual own view of the network. It can compare that to its fib and understand that in this particular case, these external IP addresses are being advertised from its neighbors, right? So the compute node is advertising these prefixes, and in this particular case, these two neighbors, it found the route in the fib, so that's good. But from this particular neighbor, this operational state is down because it wasn't able to find the route in the fib, right? So it looked in the route table and it realized that I'm supposed to be, according to Kubernetes, I'm supposed to be servicing this application from this host, but I'm not, right? And so it's able to tell you right away that the application here is down. So again, it's just a simple application. The application is not complicated, but it brings some of that context from the application world into the network world and allows for an ease of operation and troubleshooting, right? So immediately now you can export this to your take stack. You can have Grafana do all sorts of alerting and monitoring as you see fit, and you can have your switches alert on a degraded service, and you would be made aware right away as soon as the application scales up to these computes that there's an issue. You wouldn't have to wait until the user complained about a degraded service. You wouldn't have to wait until your application performance monitoring system triggers some sort of flag. Right away, from a network standpoint, you'd be made aware of the fact that you would have this issue here.
Just a quick question.
Yeah.
So I could make an argument that a RIB or FIB entry doesn't equal application service reachability. Could we have taken this a bit further with some more intelligence without compromising resources too much? Like actual application uptime type of maybe port check, TCP connection, that kind of thing?
Yeah, absolutely. So actually, we tried to get some of that in for the demo, but just didn't get to in time. But yeah, you could do things like, for instance, ensure that you have the matching ACL that allows the traffic in, right? You could potentially, if you wanted to, we have some functionality in SR Linux, which is packet trace, which allows you to play back a packet through the switch. So you could actually even go as far as ensuring that from the switch's perspective, you actually have data plane reachability beyond just knowing that it's in the fib. You could craft a packet. It's actually very simple to do, and funnel that through the box and have it return to you whether there's an egress interface for that very specific packet. So you could definitely take this as deep and as far as you want. For this particular demo, we just did a simple fib check to just kind of demonstrate the capability. But the world's your oyster. You can go as far and deep as you want with it. I didn't make this very pretty, but this was just kind of a proof point. I don't know if you can see my my window here. I had just created a very simple telemetry stack where I was just dumping basically the data that we saw from in the CLI into Grafana. Of course, in a real world, you would pretty this and alarm and so on and so forth. But the point was just to demonstrate that the data that didn't exist on that switch before the application was onboarded now exists both in the CLI, like I just showed you, but also proof point that it exists in our northbound interfaces, and mainly in this particular case, GNMI, right? So anything that I was onboarded from the Yang model standpoint is available for you to consume off box. So that could be, in this case, it's all state. So there's no configuration aspect in this particular application. I'm just retrieving state, but you're getting the network view state exposed to any of your monitoring systems. A couple small things I just wanted to show really quickly. You kind of saw me navigate the CLI a little bit. Some aspects of the CLI I just wanted to highlight in what I was showing you. So you showed me do an info command, right? And I infoed where my current application was. The displayed here is kind of like JSON-esque, but it's not exactly JSON. It's kind of like our interpretation of what looks kind of like JSON. It's also not, on a large data output, it's not very easy to read. So we put things into the CLI that allow you to kind of show this and allow for operators to get to the information they want quickly and easily and read it nicely, right? So we can take this information that I'm showing here, and we can actually massage it and output it the way we want to. So the first thing is I could do a pipe here and display it as different. So I can play it as proper JSON if I wanted to, right? So as I said, it wasn't quite JSON, it was text, but now it's looking proper, like proper JSON if I wanted to do that. But I can also go one step further, and I can start populating this data as maybe like a table. So first of all, you'll see here as I'm going through this, the CLI is auto-generated. It's suggesting to me things. It's suggesting that if I type S, that I could auto-complete service. It's telling me that under service is maybe multiple options. I can tab complete that. It actually drops down a little menu if I wanted to go and navigate it. So we'll do that. We'll keep tab completing because it's very easy. In this particular case, I'm going to match my external address, host name. You know what we'll do from all my host names. And I can pare down my information, right? And really, maybe what I'm interested in that information is not all of that. Maybe I'm interested in looking at only my oper state and my oper reason, right? So I can filter fields and only show my oper state and my oper reason for that, right? And as a network operator, I may actually think that this is a bit cumbersome to look at, and I want to format it differently, so I can actually take that output and I can format that as a table, right? And now all of a sudden, I've taken my command and I've displayed it on my CLI in a way which a human can understand. Now, obviously, I can take all this and I can alias it, so I can make this a really short command, and I can propagate that to my engineering team so that they know how to issue a command. I can make this a short command if I wanted to, but that's just a way of formatting and displaying some information in the CLI. And the last thing I wanted to show you in the CLI is something that we can do, and that is in CLI stream. Yeah, go ahead.
I was going to ask about the JSON stuff you're mentioning. What's the value of doing something like JSON but not JSON? What's the point of that?
So the value of having it. So when we display it by default as text, it's just because it's just really a visual thing. There's no difference. Like if I do text, which is the default, you can see the difference between the two. You know, in a small look, it doesn't look that much different. Sure, it looks a little better as text. Could we have defaulted to JSON? Sure, it looks just about the same, but it's just more a visual thing.
I see. It's an option. Got it. Thank you.
It's an option. Yeah. So you can select how you want to see it exactly, and you can make that as an environmental variable to always display as JSON if you want to. Right. The default is just what we call text in this case. The last part of the CLI I wanted to show you is basically the ability to monitor inline in the CLI. And that is basically doing a local telemetry stream in the CLI. So if you've navigated CLIs before, you're waiting for a state to change. You know, either you're trying to do a watch command, which is maybe at a 1 or 2 second interval. You may miss a state change between from a BGP session, for instance. What we allow you to do is actually do a local streaming telemetry on a leaf that actually shows you state changes. So for instance, I can do a monitor command. And what that's going to do is begin a monitoring and streaming telemetry on a specific path. So I can monitor kbutler, service, front end, namespace, default. Let's monitor the external address. You know what? Let's actually monitor the oper state of my service, right? So my service is degraded, and if I jump back over here. And I scale this down. Scale this down to 1. So I'm going to scale this down. And what I expect to see is, you know, as my application is scaling down, my operational state may change from degraded potentially to up. In this case, it changed to up, right? So what this allows me to do is I can subscribe to any path locally in the CLI and see state changes as it happens. I don't have to do a wash command, or I don't have to do a up, enter, as we're all used to doing to see the state change on something. I can actually do a monitor command which subscribes to a specific leaf and see it live as it happens. So if you're watching sessions bouncing, or you're trying to see what's happening in state changes, you can do that through these monitor commands.